Hello students, my name is Harish and today I am going to explain the topic electromagnetic induction. This topic is in the chapter magnetic effects of electric current. So let us start. What exactly is electromagnetic induction? The phenomenon by which an EMF or a current is induced in a conductor due to the change in the magnetic field near the conductor is known as electromagnetic induction. So basically what this line explains is that if you look at this conductor and if there is a magnetic field around it, and this if we vary this magnetic field, there will be current induced in this coil even though there is no battery. That is what is known as electromagnetic induction. Now how did people arrive to this conclusion that what exactly electromagnetic induction is? So for this, Mr. Faraday went through a series of experiments. So let us learn about his experiments. What was Faraday's first experiment? In the first experiment, he took a wire, a bar magnet, and a galvanometer. Now, as he moved the magnet towards the coil of wire, the galvanometer moved to indicate a current in the wire. And also, when he changed the direction of the magnet, okay, he also noticed that the current direction also changed, right? And he also noticed that when he changed the speed of the magnet, the galvanometer also deflect faster. So what he's trying to say is that when he kept this setup and when he moved the magnet towards the coil, there was a current inside the coil. When he moved it away, there was another current, but in the opposite direction. And also, when he varied the speed of this magnet, the deflection was also faster. Okay, so what he concluded from his first experiment was that moving a magnet towards a coil induces a current in the coil whose direction and magnitude is given by the galvanometer. Okay, what was Faraday's experiment number 2? In the second experiment, what he did was he took a wire, the same wire coil, and then he took a galvanometer, and instead of the magnet in the first experiment, here he used a current carrying conductor. Okay, and when the current carrying conductor was moved towards the coil of the wire, there was deflection in the galvanometer. Okay, so what he concluded from his experiment number 2 was that current is induced in a coil and a current carrying conductor is brought in its vicinity. Okay, only difference from experiment 1 was that here he used an electric current carrying conductor, and in experiment 1 he used a magnet. Okay, now what is third experiment? In the third experiment, he took a wire, a same setup as experiment number 2, wire, a current carrying conductor, and a galvanometer. But in this case, he didn't move the current carrying conductor. Okay, what he did was that what he observed, he just kept it stationary, and he observed that there was a deflection in the galvanometer even though the current carrying conductor was not moving. So whenever he was plugging on the current carrying conductor, switching it off, there was a electric current in that conductor. Okay, so what he concluded from this thing that relative motion between the current carrying conductor and the wire is not mandatory for inducing current in the wire. Okay. Now what he was he gave some names to this coil. Okay, so the current carrying conductor slash magnet from experiment 1, these are called as primary coil, and the current in which the current is induced means in the current in the wire where only the galvanometer is connected, that is known as secondary coil. So from these three experiments, the conclusion which he gave was that as the current in the primary coil changes, the magnetic field associated with it changes, and as this changes, there is a current induced in the secondary coil. Okay, so in case of magnet, when you move the magnet, the magnetic field changes, and on the other hand, if there's a current in the primary coil and that primary coil current changes, then also magnetic field changes. In that case, also we can notice a deflection in the galvanometer in the secondary coil. Okay. This process by which a changing magnetic field in a conductor induces a current in the another conductor is called electromagnetic induction. Okay, students. Now see, how will you determine the direction of this current? That is where Fleming's right-hand rule comes into work. So let us look into Fleming's right-hand rule. What does Fleming's right-hand rule say? Fleming's right-hand rule say that when you stretch the forefinger, the middle finger, and the thumb, basically you have to keep them mutually perpendicular. Okay, and if the forefinger indicates the direction of the magnetic field, the thumb indicates the direction of motion of conductor, then The middle finger indicates the direction of induced current in the conductor. Okay, so this is what Brownian's right hand rule is. The forefinger will be in the direction of magnetic field, the thumb will be in the direction of motion, then your middle finger will show the induced current. Okay, so if you read this line again, you stretch the forefinger, the middle finger, and the thumb with the right hand such that they are mutually perpendicular to each other. Then the forefinger should indicate the magnetic field, the thumb should indicate the motion of the conductor, and the middle finger will tell you the direction of the induced current. I hope this diagram is clear to you. Thank you.